So good morning, everyone. Welcome to the first lecture of the course, Quantum Simulations with Atoms and Photons at Bar-Ilan University. This week, we will speak about a system of coupled lasers, and we will relate it to the XY model. So this is actually the interface between classical and quantum mechanics, but I will give the quantum mechanical approach to this problem. There is also a classical approach which is related, but I will more focus on the quantum part. So I will now share my screen, and this is going to be a whiteboard lecture. Okay, I hope you can all see my screen. So lecture number 1, we will speak about the XY model and the coupled lasers. This is the topic of today's lecture. So let me give you some introduction to something that I'm pretty sure you all know. So I thought, before we speak about coupled lasers, we should actually discuss just lasers. So let me give you a short introduction about laser theory. Maybe it could be that for some of you this is trivial stuff, but I hope I will present it maybe in a way that is a little bit different than what you are used to. So laser theory. So what is a laser? So a laser is a very simple system in which you have a cavity. So the cavity, the reason we have a cavity, we want to define a specific wave, so a standing wave of the cavity. So of course you have many standing waves, but let's assume that we can neglect most of them. Okay, that's, I'm not giving a whole course on lasers, but for reasons that will become clear in a moment, we can focus on a single mode of the cavity. And inside this mode, what we have are atoms. And we can think of the atoms as just two-level systems. So there is, again, so this is the cavity mode. Okay, and then there is a two-level system, and the two-level systems are just atoms. So this is our atom. It has two states. Of course, an atom has many states, but here we focus on two states. So it says, if you want, it's like a 0 or 1, or ground state and excited state. And the two energy scales, there is an energy scale omega 0, which is the energy of the cavity, and there is an energy scale which is omega z. So omega z is the energy of the atom. And then, of course, there is a coupling. So the coupling comes because of the fact that the atoms are inside the cavity. Okay, so what you really do is you take the cavity and you plug in your atoms. You put the atoms inside the cavity. Well, this is basically the gay material. Okay, these atoms are for us the gay material, which is inside the cavity. And the light goes back and forward. The coupling itself is due to dipolar. It's a dipolar coupling. We don't have time here to discuss. Essentially, it means that whenever, say, if you have an atom that goes from the ground state to the excited state, so if you goes from the excited state to the ground state, every time that the atoms jumps down, there is a photon that is emitted. That's essentially the physics. And then the idea of the laser, that just spontaneous emission or stimulated emission, or say spontaneous emission. Well, the idea of the cavity is that when you plug in a cavity, then the photon that is emitted, instead of going away in free space and losing it, it comes back because there is a mirror. So the photons come back, and let's assume now that for reasons that we also need to discuss, the atom is again up, or maybe there are many atoms. Okay, you can think of having, say, many atoms. So when it comes back, this green photon, which is also, it's just the same, coming back, it comes back, it finds another atom. And then what happens is that now we have the effect of stimulated emission. So stimulated emission means that as soon as the other photon comes in, then the second atom goes down, and there are now emitted two photons. So we now have two green photons. And then the two green photons, again, they don't escape in the real space, in free space, but they find another mirror and they come back. So now we have, say, two black photons, and so on and so forth. So as soon as if you have many atoms that are excited in the cavity, this will grow exponentially. This year everyone knows what is an exponential curve. in the media, even non-physicists. So we certainly know what is an exponential curve. You can clearly see that every time that the photon comes in, there are two that are emitted. So it's pretty obviously an exponential thing. Okay, I think this is probably basically quite trivial, but I do want to give it a quantum, a more sort of a theoretical aspect to it. And to do that, I would like to introduce you to an Hamiltonian. Okay, so the Hamiltonian I would like to introduce today is called the Cummings Hamiltonian. Cummings Hamiltonian. And this is basically the fundamental model of a laser. We will come back to this model later on. So that's why I would like to introduce it. Maybe we don't really need it today, but it's going to be a very useful concept in the course of during the course. So what is the Hamiltonian? So the Hamiltonian is something like this. So what we want to have the cavity. So the cavity is just a boson. So we write it as omega 0 Heidegger, just an harmonic oscillator, standard second year undergraduate harmonic oscillator. That's our cavity. And you see that plus there is a spin. So the spin is going to be omega z sigma z. That's why I call it omega z. This is not the common notation. Usually it's called it just omega or omega 0. And then, I mean, these notations, omega 0, omega z, that's what I like. But be aware that in the literature, other notations are used. I like this omega z because it's coupled to sigma z. Okay. Actually, if we want to, so we need to be a little bit careful usually. So if sigma z is a Pauli matrix, which goes between -1 and +1, then we need to multiply by half, so that the difference between the ground state and excited state is exactly omega z, and not 2 omega z, right? Because from -1 to 1, there is a jump of 2. So that's why we divide here by 1/2. Again, this is a Pauli matrix. These are all details. We are not really interested in that, but it's important to fix the notation. Okay, so now that's the simple part. So just you have the cavity and the spin or the atom separately, and then you need to couple them. And depending on how you couple them, you get different models. So the Cummings models have a specific type of coupling, which is the coupling that I pictorially described in the picture before. So it's just something like this. So it's proportional to G. This is the energy scale or the rate, the relevant energy scale. And then there is a process like this that say there is sigma minus Heidegger. Okay, so what is this process? This process is a process in which the spin goes down and you create a photon. Okay, so that's basically both spontaneous emission and the stimulated emission. So it's just emission of a photon. But now, this is very important, an Hamiltonian must always be Hermitian. Okay, that's the definition of an Hamiltonian. So you always need to add also the Hermitian conjugate. The Hermitian conjugate, if you want, is the time inverse process, is the process in which you have a photon that comes in and excites an atom. So it's basically sigma plus A. So you destroy a photon and you go back to the excited state. Okay. Are there questions until this point?
So the simulated emission enhances G. So I mean, how do I say?
Okay, excellent. So stimulated emission. The way you see stimulated emission is by A. So you know that when you apply A, say on a coherent state. Okay, here I introduce a little bit more advanced concepts. I hope you all know what a coherent state is. But essentially, even a Fock state. Okay, so when you apply, say, Heidegger to the state n, you don't just get n plus 1. Okay, that's sort of the simplest. This is the simplest picture that A builds a photon. Okay, we don't need coherent states actually. Let's think about Fock states. So when you add a photon, you go from the state n to the state n plus 1. However, that's not the correct formula. The correct formula is there is a factor, and the factor is square root of n plus 1. So there is a normalization factor. And the normalization factor gives you this is the enhancement of the stimulated emission. The fact that it's already in the operator A is the fact that when you apply the operator A or Heidegger to the state n, you get a square root of n plus 1. So that's the factor of stimulated emission. By the way, the difference between quantum physics and classical physics is in this plus 1. The fact that there is a plus 1 here, that's the key difference between quantum and classical. So if n is big, then you can easily treat it classical. The reason it's n plus 1 is that if you start in the ground state, you need to, so if you're in 0, you need to go to 1. So you need this +1. Otherwise, if you were in 0, you would stay in 0. Okay. And indeed, this is the case. I mean, in classical physics, if you are if there are no excitations, nothing comes out. But in quantum physics, there are those quantum fluctuations, and this is the way that they are described. Okay. So so the question was, how do you see that stimulated emission is sort of stronger than spontaneous emission? And the answer is by this coherence factor. It's called coherent enhancement. Okay, good, very good. So I think this is pretty clear. But the reason I want to bring it here is that actually I want to solve this Hamiltonian. Okay, so what does it mean to solve? I want to study the dynamics in the Hamiltonian. So I would like to solve this Hamiltonian in the Heisenberg picture. Okay, so in the Heisenberg picture, this is actually a very useful picture to study dynamics. And in the Heisenberg picture, what you do, you study the time evolution of operators. Okay, instead of having a state that evolves, there is an operator that evolves. So the operators are a function of time. And the time derivative is given by something like I times h comma a. So the commutator between the Hamiltonian and the operator and the Hamiltonian gives you the time evolution of that operator. Okay, I hope I get it right with minus. It doesn't really matter. Actually, I think there is a minus here, if I'm not mistaken. Okay, good.
Manuel, can I ask a question?
Yes, please.
In the beginning, you specified that the frequency of the cavity mode and the atom are not need to be the same. So how this experience in the Hamiltonian? Because I don't see that there is a difference between a case that you are at the same frequency and the case with.
Excellent question. Yes. So Malachi says, well, in the picture that you draw, you assume that they are in the same frequency, right? You want to, you say, oh, I emit a photon and then the spin goes down. There is energy conservation. So you say they should be at the same energy. So, but here I'm not assuming. I'm not assuming that the cavity and the spin are the same energy. So we will see in a moment how it works. So this is an excellent question because it's going to be answered in a moment. Maybe that's the reason why I wanted to bring out this derivation, to try to see, do I really need them? Do they really need to be them exactly at the same energy, or maybe they can be a little bit away? Okay, by the way, you can, you know, probably that it's related to G. So the stronger G is, the more you can have a detuning between omega 0. But everything is coming out of this simple model. So let's leave the suspense about it. And okay, so we compute, so we need to commute the Hamiltonian that we have with A. So of course there is a minus I omega Z A. That's quite obvious. Just coming out of the commutator between A dagger A and A. This one doesn't matter, it commutes with A, and then you see that here there is another term. So there is an A dagger here. So when you commute it, what will come out is something like minus I G sigma minus sigma minus. Okay? Okay, good. So this is the first equation. Now let's look at the second equation. So the second equation now is for sigma, because you see that the dynamics of A depends on the dynamics of sigma minus. So that's why we need to now compute the time evolution of sigma minus, because they are sort of coupled differential equations. So for this we need minus I times H comma sigma minus. So we need now to commute the Hamiltonian with sigma minus. So this term doesn't matter. This term is a sigma z comma sigma minus. Sigma z comma sigma minus is actually sigma minus. So what comes out from here is something like minus I omega z sigma minus. So it's very similar to the cavity. And then there is plus I plus G, okay, times what? Times the commutator between sigma minus and sigma plus. Okay, this is now the key point. There is a commutator between sigma minus and sigma plus. And the commutator between sigma minus and sigma plus is actually what? If I can read
Sigma Z.
lips. I think Noah gave the right answer.
Sigma Z.
Sigma Z. Very good. So what we have here is something like I would say it's I sigma Z. I hope I get it right. Okay, good. So this is the key difference, times A. Okay, so if we didn't have this sigma Z, that would be a very simple linear differential equation, right? Because you have A, sigma minus, sigma minus A. Very nice, it's linear. The problem is that we have a sigma Z here. Okay, this is the problem, this sigma Z. You can't put an X, it's actually just there. So the question is now how to solve it. And the way to solve it is basically to do a weak coupling approximation. Okay, weak coupling approximation. We will come back to this weak coupling approximation later on, but it's important to know that what we are doing. And the idea of the weak coupling approximation is to assume that the effect of the cavity on the atoms is very weak. This is usually the case if you have many atoms. So assume that you have many atoms in the cavity. Here the model for simplicity assumes there is a single atom, but you can easily extend to just a sum of many atoms. Again, we will come back to it when we will speak about the Dickey model. But in that case, what you can assume is that sigma Z essentially goes to sigma Z expectation value, meaning that so even if say 1 or 2 atoms went down, it doesn't matter. The average occupation of sigma Z is unchanged. Okay, again, it's assuming that you have many atoms, so that when you come back, say the probability of finding, even if you have a drop down, say 10 atoms, when you come back, when the photons come back from the mirror, it will still see the same number of atoms which are up. Say there's still the 10 to the 32 atoms that are up, and that's the assumption. Okay. Again, we will justify it more sort of in a scaling way later on, but I think I hope it makes sense. Yes, reasonable.
Hi, Emmanuel.
Yes.
How do you define weak coupling?
So for the moment, at this moment, weak coupling, just as you hear, it's weak. When we will show the scaling, etc., we will discuss more. For the moment, weak coupling, it means that the number of atoms did not change too much. As you will see, it's actually also a matter of time. You know, how long did you wait? If you wait long enough, then because the number of photons grows exponentially, eventually we will kill enough atoms, and then it's no more weak coupling in this sense. Also, the word weak coupling itself can be defined in many different ways. I don't want to enter into this at this stage. Otherwise, we will spend the whole 30 minutes that we have on this topic. So just think of it as it's weak. Okay, I hope it's, yeah. Okay, good. So once we do that, why this is important? Because once we do that, then you look at the equation of motion. You see this equation of motion, this one and this one, and you see that they become linear equation of motion. So I have substituted here, instead of sigma Z, it's just becoming a constant, even time independent if you want. And then what you have are just linear equation of motion. So we can write them in a form of the matrix. So A, dA, dt, actually let me write it like this. So it's the time derivative of a vector A sigma minus, which is some matrix. And the matrix is going to be omega 0, omega Z. Oh, there is a minus I in front of it. There will be here G, here minus G, sigma Z. Okay. Actually, I think actually this one also should be a minus. I think also this one should be a minus. You can check at home. I think this is also a minus. Sorry, minus I. So there is a plus here. Just you need to check the commutation relation. Okay.
Times the vector.
Sorry, times the vector. Very good. Very good. A sigma minus. Okay. So it's just a linear equation of motion. So that's things that we know how to solve. And what we need to do is just to find, diagonalize the 2 by 2 matrix. Okay, that's very simple. So we need to diagonalize this matrix. Actually, because I'm lazy, let me diagonalize in a specific case, which is that omega Z equals to omega 0. So the 2 frequencies are the same. This is called on resonance. Okay, we on or resonance. So the cavity is exactly at the same energy as the atom. I will comment in a moment what changes if this is not the case. So we need to diagnose this matrix. So the matrix, okay, let's do it. So it's something like lambda minus omega 0, G sigma Z, okay? Lambda minus omega Z, and we need to take, so this is now omega 0, because omega 0 and omega Z are the same, and we need to take the determinant of that matrix and equals to 1. Okay, that's the way we find the eigenvalues. This is the eigenvalues to a matrix. I apologize if it's a little bit boring, but I want to show that because in a moment it's going to be very surprising, I think. So it means that lambda minus omega 0 squared minus G squared sigma Z, that's basically equals to 0. So this is equal to this one. Lambda equals to omega Z. Oh, there is an I. Okay, forget. Yeah, there is an I in front of this. We don't. Yeah, the I is important. But let's just diagonalize this matrix. We need then to multiply by I to get actually the eigenvalue itself. So the eigenvalue is going to be omega 0. Omega 0, right? Plus square root of G squared sigma Z. Okay, I just took the square root from both sides, maybe a plus minus if you want, and then I change, I move the terms. Okay, yes, makes sense. Okay, yes, those. Okay, good. The faces I see, they are nodding, so that's a good sign. Okay, so what's going on here? So what do we do? Why is it interesting? Do you see why? What's peculiar about this this expression here?
So when sigma Z, like average sigma Z is -1, you get imaginary eigen. Very
good. Yes, exactly. So actually, let me actually, I think it should be the other way around. So this is the advantage of graduate course. You can put minuses as you wish. People do not get upset at you. You can check the minuses. So essentially, what you see is it's also a matter of how you define sigma Z. So do you define sigma Z? What is the plus and minus 1? So I know the answer to this, so that's why I know how to put the signs. So what you see is that essentially, if sigma Z in this case is positive, then you get an imaginary part. Okay, so for sigma Z that is positive, what you see is that lambda becomes imaginary. Oh, I did it the Hebrew way. Okay, let me do it the English way. So if sigma Z is negative, is positive, then what you see is that lambda becomes imaginary. Okay, good. So let's discuss the physics. What does it mean? It means that if you have population inversion, so if there are more atoms up than down, then the lambda is imaginary, meaning that there is an exponential increase of the laser. So this laser effect requires population inversion. I think this is also sort of a basic theorem of physics, that you need population inversion to have a laser. I think from the example we saw before, from this schematic example, is pretty obvious that if you want to increase the number of photons, you need a lot of atoms up, so that every time that the photon comes in, that you have more stimulated emission than stimulated absorption. So I think physically it's very, very, it's almost obvious. However, I think mathematically it is, for me at least, very surprising. And the reason it is very surprising is that we got this imaginary term out of an Hamiltonian. So what I'm basically telling you now is that there is an Hamiltonian, and it's a Hermitian Hamiltonian, and its eigenstates are imaginary. For me, at least, I think it should be. I think if it is not surprising, well, unless you are, say, Nimrod, Nimrod, I'm not sure if he's here. Nimrod also wanted to come. So if you're Nimrod, you say, okay, good. Emmanuel, it's quite obvious this is an exceptional point. So we know that Hamiltonian that looks Hermitian, they are not always Hermitian. But I think for us that we are not as expert, I think it is a little surprising. Let me just comment in two sentences why this is the case. This is related to the fact that to define Hermitian operators, you always need to look at what happens at the boundaries. So you remember that, think of the definition of an Hermitian operator, say the derivative. How you demonstrate the derivative though? I times the derivative is Hermitian is by applying, you know, by integrating by parts so that you move from derivating on the right to derivating on the left. So you always need to have boundaries to look what happens at the boundaries. And in this case, the Hamiltonian, in our case, it's infinite because we have an infinite number of photons. And because of that, it turns out that although the Hamiltonian looks Hermitian in the sense that you wrote it as something plus the Hermitian conjugate, it is actually not Hermitian. Okay, so this is the physics of the conceptual points. Again, I hope maybe we will have time during the course to come back to this very surprising effect. But here you see an example that, you know, by just having real couplings, you can get imaginary eigenstates. Okay, very good. So the only other thing you need to add is basically in reality. So from here, what it looks like is that as soon as you have, oh, okay, sorry, one comment. So there was this question before which asked what happens if there is a detuning. So if omega 0 is not omega z, so you can still exactly solve this problem. And, you know, I leave it as a homework if you wish. You can take this matrix and assume that omega 0 is different from omega z. Then what you will obtain, instead of this very simple quadratic equation, you have just a quadratic equation of the form, you know, a lambda squared plus b lambda plus c. And what you will see is that you will, in order to have the term which is imaginary, you will need not only not any sigma z is enough. So you will have, okay, let me comment like this. If for omega 0 that is different than omega z, you will obtain something like omega z minus omega 0 squared minus g squared sigma z. You know, there may be factors of 2, but roughly speaking, this is what you obtain. So if omega z and omega 0 are very different from each other, then you never get the imaginary part. To get the imaginary part, you need that either omega 0 is equal to omega z, or that g is very big. And by the way, one possible definition of weak coupling versus strong coupling is actually this one. But, you know, that's not the one I was using here. Okay, so there is basically a resonance. You know, the resonance has a width, and the width of the resonance is related to g. So g gives you the width of the resonance. Okay, so that answers that question. The other thing one needs to add in order to understand really lasers is the fact that, in fact, you know, if you had perfect mirrors, that's the assumption here is they're perfect mirrors. So every time you emit a photon, it comes back forever, and you have an exponential growth. But of course, this is not a very useful laser because it doesn't emit light. So in reality, you use some mirrors that have a finite leakage out of the mirror. I think also part of it is that you just cannot have in reality a mirror that is 100% reflective. But even if you had it, it would be completely useless because there is no light coming out. So you always need in laser some decay, some dissipation of the photons. So the fact that the photons can escape in free space. So let's call it the photon decay, photon loss. Now, to describe photon loss, that you cannot use an Hamiltonian, right? This is a dissipative process. It's a process that loses photons. So you need to use more advanced techniques. We will not review them right now. Maybe later in the course we'll see. So you need, say, some Lindblad-Master equation, Lindblad-Master equation. I mean, there are many methods. You can use the input-output theorem, quantum jumps. I mean, there are many different methods to describe dissipation. They're all equivalent. But I'm just saying you need to do a little bit more mathematics. What you will see in that case is that you will have some additional decay term. So if beforehand we had something like dA over dt, which was minus I omega 0 A, and then there was here plus G sigma Z plus G sigma minus, there will be here some additional term. So something like, oh, there is I here. So there will be, say, minus I kappa times A. So this is, sorry, without an I. So there will be some additional decay term, okay? And then what you will see is that there is a competition between the imaginary part of lambda and the kappa. So kappa leads to a decay. The imaginary part of lambda can lead to an explosion, to an exponential growth. And so what you will need in order to have lasing, lasing requires it requires that the imaginary part of lambda is going to be larger than kappa. Okay, so that, you know, the gain, okay, in physics, in classical physics, you say the gain should be larger than losses. Again, it's quite trivial. Let me just mention so how can we describe the lasing transition? Okay, this is a concept that is going to be useful. So a way to do that is to actually take to look at the complex plane of these eigenstates. Okay, so here we have, say, the real part of lambda, and here we have the imaginary part of lambda. Let me see, is it, well, actually, the way I define it is the other way around. So, yeah, so let me draw it like this. So I want to describe here the real part of lambda. So this is just this is just the energy, okay? And this is, here we'll put the imaginary part of lambda. Oh yeah, that's good. So this is the decay. Okay, I'm doing it right, good. So an imaginary part times minus kappa. So we introduce also, we take the combined effects of the cavity and the decay. So what is the difference between, so the real part is approximately something like omega 0. Okay, that's the real part. And the imaginary part can be either positive or negative. So if the imaginary part is negative, okay, so if we are here, then we have more losses than gain. So there is no lasing, Okay, this if the eigenvalue is here. Instead, if the eigenvalue is here, so meaning that the imaginary part is positive, there is an exponential growth, there is lasing. So the transition between a non-lasing and lasing is just a transition in which you have an eigenstate that goes from negative to positive. So whose imaginary part goes from negative to positive. This picture is going to be useful in a moment. Okay, very good. Okay, questions until now?
Can I ask a quick question?
Yes, please, Jacob.
So if I remember correctly from basic laser courses, we need at least a 3-level atom to have actual lasing and population inversion. But your Hamiltonian only includes two-level systems. So how does this work?
Okay, thanks, Jacob. So this is a good question. So what I'm discussing here is sort of a transient lasing. So this is a lasing that builds up, but then kills all the atoms. And so if you kill all the atoms, eventually, it doesn't matter if you have 10 to the 32 atoms, eventually all the atoms will go down and your laser stops. What you are asking about is how do I get a steady state lasing? So to get a steady state lasing, I see somehow a process that brings back my atoms up. So you sort of a separate process that takes my atoms from the ground state and brings them back to the excited. So of course you cannot use, if you just have a 2-level system, then the way to bring them back is to use the cavity itself, but that's not allowed. You cannot put energy in the cavity and ask how much energy is in the cavity. So this is sort of not lasing, it's cheating. Okay, so the minimum is to have 3 levels so that somehow you bring the atoms from the ground state to that excited state, this sort of third state, and then they come back. So this is related to the question how you do repumping, how you get a steady state. So I would say to get a transient lasing, you can have it with two levels. To have a steady state lasing, which is what you want to have in the lab, then you need a 3rd level so that you can repump. That's basically the idea. Okay, very good. So let me summarize this part by just one equation, which is sort of a simplified version of these what we have seen now. And basically, we can think of the laser as something like this. So something like dA dt equals to think of it as let's do it like this. Square root of minus g squared sigma z minus kappa a. Okay, there is an I here. So basically there is some gain. This is the gain. So in the case of the model that we discussed, that's the gain. But in general, we can call it, say, some imaginary part of lambda. So there is some gain, and then there is some decay. You have seen that I have simplified the model. So this is sort of a simplified version. I'm going to, the reason I introduced this simplified version of the laser equation is that I want now to discuss coupled lasers. So if we still bear the spins, etc., we will, we'll get lost. So I made two simplifications. First of all, I am forgetting about the spins. I'm somehow integrating out the spins so that I'm looking at the laser itself. This is, I mean, the simplified version is sort of cheating, okay? But it's cheating. We need to cheat, otherwise it becomes too complicated. So that's simplification number one, that I'm just sort of plugging in already the spins. I'm sort of integrating out the spins, but I'm doing it in a cheat. One can do it formally. I mean, you can see in the books, but for us, this is good enough. And then the second approximation I'm using is to actually assume that I am in a rotating frame. So you see, I am, so it's a rotating frame. The rotating frame simply means that I'm assuming that A equals to some A tilde e to the I omega 0 t, in a way that I get rid of the omega 0. So the equations of A tilde, if you want, these are sort of equations of A tilde, and in the equations of A tilde, you get rid of the constant. So it's like just shifting to a rotating frame, so you're shifting to a constant frequency. This is a very common trick in optics. Usually this frequency is very high. Say if it is a laser, so it could be an optical frequency which is very high. So these are the two assumptions that I'm using, so that I can summarize with something like this equals to something like A alpha A tilde. Okay, so there is, for a single laser, it's just this very simple differential equation, and then alpha can be either positive or negative, whether it is a laser or not. Okay, and again, I haven't really shown the whole derivation, but I think morally, I hope you are not too annoyed. Okay. Good. So now we want to move to coupled lasers. So for coupled lasers, what I want to do is something very similar. Just want to assume that there are, say, many differential equations. So we have dAI dt equals to alpha I A I. Let's even make our life simpler. And let's assume that these are all the same. So we have many lasers. Okay, so these are just many lasers. It's just the same equation multiplied many times. Okay, that's sort of trivial. But what you can do, you can couple them. Okay, so the interesting part is that you can couple them, and that's, I think, there's Neil Davidson, who I can see here, was a pioneer in this field. I think, I mean, the idea of coupling two lasers is something that, I think it's probably an old idea, but the idea to actually try to couple many lasers, I think that's something new, and especially putting it in the framework of simulations and quantum simulations, that's something that was really pioneered in Weizmann. So the idea is, so in terms of the equations, the basic equation, you have some coupling, okay? So these are linear equations of motion, and you just assume that there is some coupling between the laser A and the laser J. So something like this. It's very simple. Okay. So now, what is useful now is to discuss two types of Cij. Okay. So what I want to do now is to characterize Cij as into sort of, to split it in sort of a real and imaginary part. So a little bit like before that we had the eigenvalue and we look at the real and imaginary part, I want to do the same for a matrix. So I want to discuss the sort of the real and imaginary part of Cij. So actually, let me start with the imaginary part of Cij. The imaginary part of Cij is basically a part for which Cij equals to minus Cji star. So sort of it's her anti-Hermitian part of the matrix. In general, Cij could be any general matrix, and like a number, you can split it into real and imaginary part. The same way, you can take a matrix and split it into Hermitian and anti-Hermitian part. It's exactly the same idea. So let's look at this sort of anti-Hermitian part. Okay, the anti-Hermitian part will always have pure imaginary eigenvalues, and okay, and Now, so first, let me discuss how can you create such a coupling physically. What does it mean? So physically, it basically means that you have a coupling in which you have photons that jump from one cavity to the other. So think of a sort of a mirror. Okay, you have, say, two cavities, and there is a mirror that brings photons from one cavity to the other, something like this. So you have two cavities, then there is a partially reflecting mirror and another partially reflecting mirror. So if you put photons in the cavity one, say this is cavity one, cavity two, the photons can move to the cavity two and vice versa. Okay, so this is this pure imaginary. It's the pure imaginary. Okay, I see that for being consistent with what we did before, I think actually let me a little bit change the notation. Yes, okay, yeah, okay, let's go this way. Okay, so what does that mean? Okay, so in terms of the eigenvalues, it's pure imaginary. So it means that these are sort of just the solution will be periodic function, right? This is something like e to the I, say, let's call it epsilon t. So this is the part that makes oscillations in these equations of motion of the coupled lasers. I discussed that physically how it happens. So how can we describe it in quantum mechanically? The way to describe it quantum mechanically is something like, so what will be the interaction? It's something like this. So it's something like, say, let's call it T AI AJ plus emission conjugate, and there is a digger here. So it's a process that takes a photon from one cavity and brings it over to the other cavity. You see, you destroy a photon from the site J, from the laser J, and you bring it to the laser I. Okay, and when you take this type of coupling and you write the equation of motion in the same way that we did before, what you will see is that you get something of this type, actually, of this type. Okay? So if you want to physically realize a pure imaginary coupling, what you need to do is to engineer a way in which photons can jump from one cavity to the other. And in this case, what you will say is that the eigenvalues are oscillating. Okay, that's possible. However, that's not the route that Davidson and colleague followed. They instead actually looked at another type of process, which is a process that is related to the Hermitian part. So let's actually now discuss what happens to the Hermitian part. So the Hermitian part is a part for which Cij equals to Cij star. Okay, so this is actually pure real. So, okay, real will lead to real eigenvalues. And so it's going to be something like e to the epsilon t, something that grows exponentially with time. So this is a dissipative process, but it's a coupled dissipative process. Okay. Now, how to realize that in experiment? I'm pretty sure that Nir will discuss it in his colloquium. So I don't want to, I will try to give you my understanding of that. Nir, if I'm saying something completely wrong, please correct me. And if I'm okay, yes, you're listening, very good. So if I say something wrong, correct me. And I'm sure if you don't, but don't worry if I say something wrong, because anyway, Nir will correct it in his colloquium. So don't worry too much about it. Let me nevertheless, sort of for completeness, try to tell you how I understand what's going on. So what I understood is that the way they realized it, actually, they have sort of a common cavity. That's something like this. So what you do, what they do is you take sort of a barrier like this. So in a sense, you allow you allow the cavity, instead of the light, instead of exploring the whole cavity, just to have only two possible modes that are allowed, which are spatially separated. But then you put, let's say, a small lens. I know this is not exactly what they do, but something like this. You have a small lens, and then what happens is that you can tune. So you see, if you can, using the lens, you can deflect, say, the orange light. And one possibility is to deflect the orange light so that it goes exactly to the red light. This will be like an imaginary coupling. But what they do instead, they deflect both, and then they direct them actually on the mask itself. So they let the orange and red meet on the mask. And the mask is bad because it absorbs light. So this is actually a dissipative process. However, there is a way to minimize losses. So there is a way to find an eigenstate that has a good gain, that the losses are small, if it occurs that the orange and red line are exactly out of phase one of each other, right? So if there is a destructive interference when they meet on the mask, there is actually no light on the mask because they exactly interfere. And then in that case, you will see that, so there is less gain, and less gain means, less loss, and then there is more gain. Okay, so you actually engineer the losses in such a way that the losses are minimized when there is, say, a specific phase relation between orange and red. And again, by playing with the lens, you can put any phase difference that you want. So you can have a situation in which actually, conceptually, the simplest idea is to have a situation in which there is a minimal loss for orange and red that are in phase, for in phase lasers. But again, using lenses, you can just, you can plug here a phase difference. So think of adding here some phase difference in your lens. Okay, here there is some phase difference, so that when they are exactly in phase, then it comes out that there is a destructive interference on the mask, and then that's the minimal loss. Okay, again, it's much more, schematically, I think it is correct. How you do that physically, Nir will discuss it. And also there is a question, if you just have two lasers, then you can couple them. But the question is, if you have many lasers, how do you couple them? So do you couple, say, just nearest neighbors, or do you couple actually all to all? And I know that they were able to realize both cases and even cases in between. Okay, so that's roughly speaking the idea. So now comes so this is in terms of the equation of motion. Okay, so what we discussed are linear equations of motion. These are our linear equations of motion, and we understand that at least theoretically one can engineer these couplings so that there is either a real part or an imaginary part. They correspond physically to different experiments, but there are experiments like this or like that. This is still not, this is part of the story. This is sort of the simple part. Conceptually, the more interesting part is actually to map this to an Hamiltonian problem. Okay, look, this is a dissipative process. In particular, if you have a real eigenvalues, so it comes because of losses. But what you say is the following: you say, well, you see, let's actually focus on this case. Let's focus on the case that C is Hermitian. Okay, so let's assume that C here is Hermitian. C is Hermitian. Again, you need to, in practice, in an experiment, it's not easy to make that only Hermitian, but let's assume that you succeeded. So what you have is, let's rewrite our equation of motion. So it's something like the AI dt equals to alpha, say 1 times AI. So this is just the gain, just a unit matrix. This is the gain of each single Hamiltonian, plus we said Cij, Aj. So you look at these equations and you say, but wait, Cij is actually real. So what I can really think of, and you can even, you can even combine those two together. Of course, Cij is Hermitian. The one, this is just a unit matrix is of course Hermitian. So you can combine those two and you can say, oh, there is an Hermitian matrix. So let's call it Hij. Okay, so you now write dAij dt equals to Hij Aj. Okay, of course, this is sum over J. Okay, so this is something that looks a little bit like Heisenberg. It looks a little bit like a Schrödinger equation. Okay, where AI are your wave function with one important difference. What is the difference? What is missing from Schrödinger equation?
It's imaginary time.
Yes, there is no I. Okay, so this is a little bit like a pure imaginary Schrödinger equation. Okay, so here comes the conceptual idea. The conceptual idea is the following: our system of coupled lasers what is doing, there are all those modes. So let's assume that we diagonalize Hij, and we find all the eigenstates. Each eigenstate will have some exponential enhancement. Now, there is one of the modes that have a maximal exponential enhancement. So let's look at the mode, okay, where with maximal eigenstate, eigenvalue mode. There is a one mode that has a maximal eigenvalue. That mode will be exponentially enhanced much faster than all the other modes. Okay, and again, this is now a concept that until last year only optical AMO physicists knew, and now everybody knows that when there are mutations, the one that is that has the largest exponent is the winning one. So everyone knows about mode competition, and this is exactly what happened here. So eventually, if you wait long enough, what you will see is always the maximal eigenmode, the mode with the maximal eigenvalue. So okay, so at long times, it dominates. Okay, so if you just wait some time and then measure, what you will see with say 100% certainty is that particular state. Okay, so now you can translate this into an Hamiltonian problem. You can say, actually, what I'm doing, this is equivalent. Okay, that's the simulation. That's what the simulation come from. Okay, this is equivalent. This is equivalent. Okay, equivalent to what? To finding the ground state of some system whose Hamiltonian is Hij. It's not. We are not finding any ground state here. It's a dynamical problem, but it's a dynamical problem that it's linear, and it's equivalent to finding the ground state of some Hamiltonian. Right? Because what is finding ground state? If you want minus, okay, let's put the minus. So the ground state is a state with the minimal energy. Here we are finding the state with the maximal eigenvalue. So it's like finding the ground state of minus that Hamiltonian. Okay, very good. So that's really, you know, this is really where quantum simulations come in. So I have a classical problem, or even sort of a quantum classical problem of lasers, and I map it into a quantum problem. Okay, good. So we have still say 10 minutes or so. So let me a little bit discuss about the specific model that they are realizing. Okay, about this sort of linear model. So this model, let me actually rewrite this Hamiltonian. Okay, so what is the Hamiltonian? Okay, actually the Hamiltonian is you can think of it as follows. The Hamiltonian is something like, so what, okay. So our Hamiltonian, what is the Hamiltonian? So the Hamiltonian, so it's a linear system, and there are those couplings, these Hij. So the Hamiltonian is going to be something like sum over Ij, Hij, A dagger I, Aj. Okay, this is, if you want, in the second quantization language, that's how it looked like. Okay, so this is the Hamiltonian, and the Schrödinger equation, as we mentioned, is the same as this equation, but with an R. Okay, so let's move. So I would like, let me put a title here. So my title is going to be the XY model. Of course, I hope we could discuss much more about the XY model itself, but maybe we will do that in the following lectures. So a convenient way to describe this Hamiltonian is to move to a number and phase relation. So basically just to write, instead of Aij, to think of it as some Ai, absolute value times e to the I theta I. Of course, here there is plus emission conjugate, as we discussed. But the parentheses should be like this. Okay. So what we do, we instead of using these complex values, complex valued A, we use a real absolute value and phase. And so you can rewrite this Hamiltonian as sum over Aij, Hij, Ai, Aj, cosine of theta I minus theta j. Okay, this is basically it's called the XY model. The reason why it's called actually to make it an XY model, what you assume is that these Hij, you assume them to be a constant, or you don't try to minimize them. So of course you can make the Hamiltonian bigger by just increasing Aj. That's quite obvious. That's not the interesting part. This is just telling you that you can make, if you make the wave function bigger and bigger, then the Hamiltonian will be, the energy will be bigger, but you need to fulfill the normalization condition. So due to the normalization condition, we can actually essentially put Ai and Aj to 1. Okay. Again, I'm a little bit chipping and sweeping some details under the carpet, but for the moment it's good enough. So let's assume that it's constant in 1. And actually the degrees of freedom that you have is these theta I and theta j. Okay, so theta I and theta j are the phase of the laser. So they have really a simple physical interpretation. They're just the phase of the lasers at a site I and site j. And remember also that there is a minus here. Okay, so remember that that there was a minus. We are looking for the ground state of that Hamiltonian with a minus. So what is the ground state? So now it depends on Hij. Okay, so there are and again here, in the experiments you can do whatever you want. You can, at least in principle, you can couple neighboring ones. You can have Hij that have the same sign or that have opposite sign, as we discussed. Whether depending on whether there is a constructive or destructive interference, this Hij can be positive or negative. You can even put some of them positive, some of them negative. So the model, the most famous model is a model in which basically the sort of the canonical XY model. First of all, why it's called XY? It's called XY because these theta I's are, because this is equivalent to a problem in which you have spins that are on a plane. Okay, and the spins that are on a plane, you can describe them by an angle. So the angle, so it's called XY because the spins cannot, in general, a spin can point in any direction. But if you assume that the spins are only on the XY plane, then you can describe it by one angle. So it's called the XY model because you have one angle per mode. That's, if you want, the definition of an XY model. One angle per mode. Okay, so the XY model is a canonical XY model. So what is the canonical XY model? If, say, Hij equals to 1 for nearest neighbors on a regular lattice. Okay, so there is a lattice, so you assume that those lasers are on a lattice and you couple on in a neighboring one. And the lattice could be, in that case, in the experiment, it's two-dimensional, but you can, at least in theory, you can write the XY model in any dimension you want, 1, 2, 3. Okay, so that's sort of this is I would say the canonical XY model. So what is the ground state of the canonical XY model? Anyone wants to guess? I mean, give the answer. Again, I have theta I and theta j. So each rotor, it's basically a rotor can point in any direction. The energy is proportional to the difference to the cosine of the difference between the angles times a -1. Hij are all 1. Okay, so let me rewrite the Hamiltonian. So the Hamiltonian is basically just sum over I and j that are nearest neighbors, cosine theta I minus theta j, with a minus in between. What is the ground state?
The ferromagnetic.
Yes, very simply. The ground state, the classical ground state is that theta I is just a constant. They all point in the same direction. So it means that all the lasers in this case have the same phase. So that's just the ground state. Okay, in the canonical model, it means that all the spins point in the same direction, which you can think of it as a ferromagnet. it's called XY ferromagnet. That's why, because again, the spins point in the XY direction. Okay. So let me give you two sort of theorems about this canonical XY model so we'll in the last 5 minutes. Let me give you two. Again, I hoped I could show them to you, but I won't. So let me give you two statements which are quite important, and maybe I'll leave it as a homework to actually demonstrate it. So theorem number 1 is if you consider this Hamiltonian, this canonical XY model at finite temperatures. So not the ground state, we said all the systems pointing in the same direction. But if you consider it at finite temperatures, what will happen is that at finite temperatures, the theta I minus theta j start to fluctuate, right? Instead of having all the thetas as exactly in the same direction, they start to fluctuate. What happens is that now it means that there is some angle phase difference between two neighbors. Now the question is, what if I take two rotors that are far apart? So the temperature, let's say, is small. The temperature small means that there is a small phase fluctuation between neighbors. But the question is, if I take one which is on the left and one which is on the right, are they still sort of somehow related or correlated, or is the correlation completely lost? Now, in 1D, it's very simple to see that in 1D, they will always be uncorrelated, right? Because in 1D, let's assume that the first rotor points in one direction. The second one points a little bit small, the direction is a little bit different. And then the other one is a little bit different, and the other one is a little bit different. And you easily see that until you get to very far apart, the direction is completely lost. Okay, so I think it's very easy, even without any equations, that in 1D, there is no long range order. Okay, just because a small fluctuation summed over many lattices, it was a sum up to 1. I mean, to 2 pi, whatever. It's quite obvious. In 2D, it's less trivial, right? In 2D, why? Because in 2D, you say, well, maybe this one doesn't have a lot of fluctuations, but you cannot just rotate it as you wish because there are the other ones. So you sort of, the correlations have an easier way to go around. You cannot just scramble, you cannot just easily scramble it because there is another path that there is a sort of a stiffness. You cannot just rotate as you wish. However, also in 2D, actually, there is no long range order. It is only in 3D that there is long range order. Okay, so this is actually a theorem, and it's called the Mermin-Wagner theorem. And I will give it as a homework to demonstrate the Mermin-Wagner theorem. It just tells you that if you take this Hamiltonian, it starts from this Hamiltonian, you assume that the Hamiltonian is a thermal equilibrium, and you will see that there cannot be any long-range order in 1 and 2. Okay, so that's important because I'm pretty sure Nir will mention it because their experiment is in 2D. So in principle, if you have a system at finite temperature, you should not be able to see long-range order. However, there is a caveat. What I told you is that the dynamical system that Nir realizes is like finding the ground state of that Hamiltonian. How do I know that imperfect? So of course the experiment has some imperfections, but how do we know that imperfections in the experiment are equivalent to a thermal state? So the mapping was done from the ground state. We know that the experiment, the ideal experiment is like a ground state Hamiltonian. But what we have not shown is that the trial experiment, the noisy experiment, is like a thermal state. There is no direct mapping. So this is a question. Maybe what we know about systems equilibrium does not apply to non-equilibrium systems. So the Merman-Wagner theorem, there is no proof that it should not work in the experiment. So this is so that's statement number 1. Statement number 2, which is I think important for Nir's talk. Statement number 2 okay, it's related to sort of the presence of vortexes. So this is specifically in 2D. So what you can have, let's assume that you have, say, let's assume that you have something like this, so a ring. Okay, let's assume that our lasers sit on a ring. So they're coupled to each other and they sit on a ring. Okay, now what you can ask yourself is, let's assume that I start here up. Now I move to the next spin, it also starts up, it's also up. So in this case, let's say I'm 0 temperature. Okay, so they are all up. They're all coupled and they're all up. That's at 0 temperature. What can happen is that if you want, what you can have, you can prepare those spins in a way that when you go around, you actually, the spins rotates a little bit. So you know for sure that if you start up, you need to end up because it's the same spin. So if you start, actually, let's not speak about up and down. These are on the XY plane, okay? So let's say that this spin points forward, okay? This is forward. So when you do an entire circle, you are guaranteed that you should still point forward. However, what could be is that while going around, the spin rotates a little bit. So let me choose another color. And you see, let's assume that they rotate a little bit. Every time it rotates a little bit, okay? They rotate a little bit. And when you go around, you make an entire circle. Okay, so this is called the vortex. And as you can see, it's quantized. So you can have, when you go around that sort of disk, you can either acquire a phase of 2 pi or acquires a phase of 4 pi. But you are sure that it must be a multiple of 2 pi because you come back to the first state. There is a periodic boundary conditions. Okay, so what you will see in Nia's talk, there will be an experiment in which they take a ring of lasers which are coupled, and then they will discuss those excitations. So they will discuss situations in which, let's say, either all phases are fixed to 0, say, or situations in which the phase rotate a little bit, and when you come back, you actually performed a circle of 2 pi. Okay, so this is called the vortex, and he will describe vortex physics. Vortex physics, last minute, vortex physics is related also to something called a Kosterlitz-Thouless phase transition. And again, we really don't have time to go into that. So, in fact, let me just conclude by saying that there is what we mentioned that according to the Magnum invariant theorem, there is no long-range order in 2D. Okay, that was the theorem. You can think of this theorem as also as the follows. You can think of this theorem as saying that you can have many vortices. You see that every vortex is sort of messes up the phase. You have many vortices, then the phase look to you random. So the fact that you can have more and more vortices can be, it's related to the absence of long-range order. Okay, so that's okay. That's I wanted to do more, but I also wanted to give you some sort of very basic understanding of fundamental Hamiltonians. You see how what I would like to do in this course is to show you some basic Hamiltonian that you can map to real experiments. So that's why I wanted to focus on this Cummings model. Although, as you see, eventually maybe this is classical physics. I could have started just by telling you, by the second part of the talk, but I wanted to relate it to quantum mechanics also from a fundamental point of view. Not only eventually, we sort of came back to this mapping to an Hamiltonian problem, but I wanted to show you that actually it also starts as a quantum problem. So in this sense, it is a quantum simulator. Okay, so thank you for listening. And I'm now sharing the link to the Zoom meeting where Nir Davidson colloquium will take place. It should start soon. If you have questions, I can stay here a couple of minutes more and then we'll move. But I suggest that you start moving. Let me share this link. Okay.